Every time okay. Welcome. As you know, today is technically the last day of classes of the semester. It ends at midnight tonight. So we made it. What questions did you bring with you tonight? What are you worried about?
Okay.
Standing waves?
Yeah, there's a specific section on.
I don't know.
We're talking about the difference between transverse wave and
Longitudinal waves.
waves. Yeah.
So transverse waves are waves like that. The standing waves, remember, are two traveling waves passing through each other, one going left and one going right. But as these waves are going left and right, the thing that's carrying the wave, that's these bars, are moving perpendicular to the wave, up and down. That's what transverse means, is perpendicular, okay? Longitudinal standing waves, the only kind of longitudinal standing waves that we've seen are either in organ pipes or in that aluminum rod. We set up a longitudinal wave in that as well. And so in every longitudinal wave problem that is not an aluminum rod, we would have the speed of sound as our velocity. So let me just point out some things that I think will be useful. Well, that's just let's. That works for everything. Traveling waves, standing waves, transverse waves, longitudinal waves, any kind of wave you can think of, that works. That works for all standing waves. This is all waves. And then if we have longitudinal, actually just any longitudinal waves, whether they're standing or traveling, those are going to be sound waves where speed is just 343 meters per second. Okay. For transverse waves, whether they're standing waves or traveling waves, the speed is going to be equal to the tension divided by the mass density, where the mass density is just the total mass divided by the total length.
In what circumstances will the football equation change with open closed versus open on?
Just a second. I'm sorry. Is it Alex?
No.
No, I'm sorry.
Darren. So in what case would the football equation change, or like how do we use it with open, closed systems.
exactly the same. That's the beauty of it, is that you don't have to make any changes. For example, if I had open,
Like 1 point.
and I had the third harmonic,
Just look up.
there would be 3 footballs. Okay, and the formula, remember, is number of footballs times lambda over 2 is equal to L. So I would just plug in 3 for the number of footballs. And then if I knew the length of the pipe, I could find the lambda. If I knew the lambda, I could find the length of the pipe. Now, if the third harmonic were in a closed open tube, that would have 3 half footballs. And so I would put in 3 half footballs times lambda over 2 is equal to L. And if I knew L, I could find lambda. If I knew lambda, I could find L.
Yeah.
Now, the key is looking at how things started with organ pipes. If it's open, the longest wave that will fit has 1 football, and that's F1. Every time you go to the next allowed resonance, you have to add a whole football. And so we go from that to 2 footballs. There's 1 football, a half, that's 2 footballs, that's F2. And then we go to 3 footballs. And so forth. For the closed open, we start with half a football. And because that's the lowest frequency, we call that F1, or the fundamental, the lowest that will resonate. And then each time I go up, I have to add 1 whole football. But here, when I added 1 football, I was doubling the number of footballs. Here, when I add 1 football, I'm tripling the number of footballs. I'm going from a half to 3 halves. So that's F3. Okay. And if I add another football, now I've got 5 half footballs. And that's F5. So if this was 100 hertz, this would be 300 hertz, and this would be 500 hertz. Now, I hope you're seeing what's forcing this, and that is the grand high wave equation. This is staying 343. If I'm cramming 3 times as many footballs into the same tube, those footballs are 3 times smaller, are they not? And that means the wavelength is 3 times smaller, right? Well, if this gets smaller by a factor of 3, this has to get bigger by a factor of 3 in order to keep this 343. Okay, it's give and take. One gets smaller, the other one gets bigger. And that's why if you've got a closed open system like this, the 23rd harmonic, if you drew that pattern, how many footballs would there be in there? Did you say 23 halves? Because you started in a closed open system, you started with half, the 23rd harmonic has to have 23 times that many footballs. Well, 23 times a half is 23 halves, which would be 11 and a half footballs. On the other hand, if you had a transverse standing wave on a guitar string, well, the first harmonic, since you're going from node to node, is going to have one football. The 23rd harmonic would have 23 footballs. 23 times as many as you started with is the key. So rather than memorizing, well, I do halves on this one, I do fulls on those, it just, whatever you start with, the 23rd harmonic has 23 times what you started with. Okay?
Can we talk about the Doppler effect next?
Doppler effect, sure.
There's a good question. Another sample exam, question number 9.
Yes. These Doppler effect problems are often best visualized with a graph where I'm graphing frequency versus time. So if my source, say the siren on the car, is always making 400 hertz whine, the Doppler shift is just how much different the frequency is that you're hearing from 400. And in this case, that car is coming towards you or away from you?
Okay, it's kind of long. It like says straight towards you, slows down gradually and stops next to you. As the car is slowing down, does the frequency decrease, increase, or stay the same?
Okay, so it's coming towards you. Is the shift going to be above 400 or below 400? Above. Okay, so I'm going to hear something higher than 400. Let's say 410. That depends on how fast the car is going. Okay. And so if this car came at me always the same speed at 60 miles an hour cruise control, I would be hearing 410, 410, 410, 410, 410. Now, be careful with your language. That is shifted up higher than what the siren is making, the 400. You're hearing something higher than 400. But if I asked you, what's that frequency doing during the next 5 seconds? Well, it's 410, 410, 410, 410. If that was your bank account, what's your bank account doing? It's staying steady. Okay. It's elevated from what the siren was making, but it's still staying steady. But if that car is braking, it's going 60 miles an hour, then 50 miles an hour, then 40 miles an hour, 30 miles an hour. This shift is going to get smaller. Okay, instead of being 410, it might be 49, 408, 407, 406. And eventually, when that car stops next to you, actually, when it stops, regardless of whether it's next to you or in the next county, when it stops, if you're still hearing it, if your ears are that good, you're hearing 400. Okay, it's only the speed that matters.
So the direction of the frequency matches the direction of acceleration.
No. So, let's say it's going away from you. And it's speeding up. What's gonna happen to that shift?
But if you set up your grid system to where you are always positive, accelerating negatively.
You're gonna get yourself in so much trouble doing that. Yeah, you're just gonna get yourself all twisted in knots. All you gotta remember is the shift is up if it's going towards, down if it's going away, and how big the shift is depends on the speed. So just do the dots. If this is going away and speeding up, that shift is gonna get bigger and bigger. So that would be going away, speeding up. If it was going away from you and slowing down, we had that in one of our homeworks. This would be coming towards and speeding up. And you can see that the shift is getting bigger. Remember what the shift is. The shift is how far away it is from 400. Okay, and then this one would be, as we said, coming towards and slowing down. Okay. How big the shift is depends on how fast either the source is moving towards you or you're moving towards the source or away.
I have some questions on like the spring tokens where they're coming together and one is like on the edge and then it reflects and it. The first sample exam.
Uh-huh.
Where it's like, where did this initially start? Where did them initially get started?
Okay, if we remember the full story, and the full story is you're seeing chapter 2. Okay. In chapter 1, the incident pulse, the mother pulse, comes to the boundary, the hospital, and splits, giving birth through division. Okay. Splits into what I call the twins. And some of the pulse goes into the other spring, and some of it reflects back into the original spring. And so what you're seeing is a picture of the twins scurrying away from the hospital. Okay, mom's already come to the hospital and split. Okay, so both of these started right there at the boundary at midnight and started scurrying away. And so immediately I can see that this is the fast side and this is the slow side. There's two ways to see it. One is, well, it just got further away from the hospital. The other way is it's wider. Okay, so this one's got to be the fast one on the right. Now you remember going back to the 12th tutorial, not this week, but the week before, that when a pulse hits a fixed end, it flips and comes back. When it hits a free end, it doesn't flip. It just comes back on the same side. Well, the same thing's gonna happen when the mother pulse, the incident pulse, hits that boundary. Okay, if that boundary is acting like a fixed end, the reflected pulse is gonna be inverted. It'll switch from one side to the other. If the boundary acts like a free end, it won't invert. Now the transmitted pulse, the pulse that goes into the other spring, never inverts, never, ever, ever inverts. Okay. So if I see these twins on opposite sides of the spring, one's on top and one's on bottom, the reflected pulse is flipped. Okay? And that means that that boundary acted like a fixed end. Now, when you see slow and fast, I want your head to be saying heavy and light. And then I want your head to go further and say really heavy, lead chain, really light, fishing line. Okay? And then ask yourself, which way is it going to act like a fixed end? If I'm coming in on the fishing line and hitting the lead chain, or going the other way and hitting the fishing line? Well, it's coming in on the fishing line and hitting the lead chain. So the mother pulse had to have come in on the fast side. And that means that this pulse here is the reflected pulse. You remember, this one's going this way, this one's going that way. And that means that the mother pulse had to come in on the bottom. Why? Because when it hit that boundary right there, it flipped. And the reflected one's on top, so the original had to be on the bottom. Okay, and then the transmitted one is that one, and you see it didn't get flipped. It's still on the bottom like the mother.
Is the fast end the one that's usually gonna be the incident pulse? Like,
I'm sorry?
is the fast end usually gonna be the one that it starts at the incident pulse?
Oh, no. Can be either one. When you look at that picture, if they're on opposite sides, if one's on top and one's on the bottom, then it definitely came in on the fast. But if they're on the same side, either they're both on top or both on bottom, it came in from the slow side. Okay?
Could you please do a plain one?
I'm sorry?
Could you do a plain question, please?
Oh, certainly.
Just been like a.
Lane.
So
Really no.
are there any more questions on these transmission reflection problems? You're good? Okay. There are two different flavors of the plane problem. One is let's start over here. We've got this plane, and it is some height above you. And by the time it travels some distance x, the Mach cone that gives you the baboom has reached your ears. So one variation is you're given the speed of the plane and asked about distance. How far does it go? How high was the plane? Something like that. Okay. So to solve that kind of problem, you first of all find the Mach number, and that's just the speed of the plane divided by 343 meters per second, speed of sound. Okay. So let's say the Mach number is 2. That'd be a speed of the plane of 686 meters per second. Okay. Then the next step is we find theta. Okay, and we know that the sine of theta is equal to 1 over the Mach number. And that means theta is equal to inverse sine of a half, which would be 30 degrees. Okay. Well, now, if I know that's 30 degrees, if I tell you the height is 1 kilometer and ask you what x is, you can do that. If I tell you that it goes 1.7 kilometers before you hear the ba-boom and ask you how high it is, you can do that. It's just trig. You know, this is the opposite side, this is the adjacent side, and the tangent of 30 degrees is going to be the opposite side over the adjacent side. Okay? Just a second, I'm almost there. Now, the other version is the opposite. Okay? You are given the distances and asked to find the speed of the plane. Well, let's look at that case. If I tell you that this is 1 kilometer and this is 1.7 kilometers, it goes 1.7 kilometers before you hear the ba-boom. Well, now the first thing I've got to do is find theta from those distances. So theta is going to be the inverse tangent of the opposite side over the adjacent side. And the inverse tangent of 1 over 1.7 is 30 degrees. And then I would say, well, the sine of theta is equal to 1 over Mach number. But what I want is the Mach number. So I'm going to cross multiply and say the Mach number, which is V plane over V sound, is going to be 1 over the sine of 30 degrees. So in both of those problems, you're using the sine and the tangent, just in different order, depending on what you start with. Okay.
Will you ever have a Mach number that's in between a whole number like 2.5 or anything like that?
Yes. Yes. Indeed. It turns out that if you remember, I told you in class that there's a simple-minded way that doesn't use that equation with the sine of theta. And if you do it that way, you'll get the wrong answer. Well, the faster the plane's going, the more likely you are to get close to the right answer with the dumb reasoning. Okay. So in my problems, the plane's either going to be going 1.1 or 1.2 or 1.3 or 1.4 or 1.5 or 1.6, but never 2.5. Yeah. Because if I keep it between 1 and 2, if you do it the right way, you get one answer. And if you do it the wrong way, you get something way the heck and gone. Okay.
Question had to do with simple harmonic motion and how the amplitude is affected when we increase, when we double the amplitude size, how that affects the other variable.
How that affects what?
How the other variables are affected when we change the amplitude.
Oh, what we learned in class was that the timing is not affected at all. So if these are the turnaround points, this would be x equals a and x equals minus a. You know that the total energy we can write in three different ways. The general formula that always works is just the kinetic energy in the block plus the potential energy in the spring. That's always true. At turnaround, either here or here, I have to stop to turn around. And at the turnaround, delta S is equal to A or minus A. And so delta S squared is going to be capital A squared, right? That's a turnaround. And then I also have at equilibrium, the spring is neither stretched nor compressed. Delta S is 0. And V is equal to V max. At the turnaround, delta S is equal to A and V is equal to 0. So now all the energy is in the motion of the block. So if I double the amplitude, I'm increasing the energy in the system by a factor of 4 because it's squared. The timing doesn't change. We found that was the simple harmonic motion. It's still going to take just the same number of seconds to get back and forth. But if the energy is 4 times bigger, then when it goes through equilibrium, if it's got 4 times as much energy, it's got twice the velocity. So that twice the amplitude is going to double the speed in the middle. Okay. And but the timing that's changed.
With the football question or equation, with the lambda, does that give us the wavelength of that frequency or that harmonic? Or of the fundamental?
Oh, that football equation, when you put down in that equation the number of footballs, you've picked a harmonic. And that's the wavelength of that harmonic. And when I plug that into my wave equation, V equals F lambda, that's going to give me the frequency of that harmonic. Yeah. Yeah. Once you've put down the number of footballs, you've picked a harmonic. Choose wisely.
With a longitudinal standing wave in our tutorial yesterday, it asked how to know when a molecule is going either like contracting in on a node or expanding on a node. Could you explain how you think of that and what your trick is to figure out?
Yeah. The key there is looking at the nodes. Let's say we've got the third harmonic going on. Now, as I said in class, this football notation is really, really crummy for longitudinal standing waves. It's really good for transverse standing waves because you could see the footballs happening. You know, as things went up and down, you saw where the antinodes were and the nodes, but in a longitudinal, things are sloshing and nothing's going up or down. And so the football notation just tells me where the nodes are and where the antinodes are. Now, for a transverse standing wave, the node would be right there. That's the point in the string, say a guitar string, that's not moving. But for an organ pipe, when I say the node is there, I mean there's a whole layer of particles all the way across that tube that aren't moving, that are at a node. And likewise here, there's a whole layer of gas particles that are not moving. Now the standing wave is just the crunching and deserting and crunching and deserting of these nodes. And if I tell you that this particle is moving that way, when I took this picture, I suddenly know the motion of all the other particles, okay? I know that this node right here is in the process of being deserted. And so all of the particles in this football over here are going away from that node. And the fatter the football is, the bigger the displacement away from equilibrium. So at the antinode, they'd be moving the furthest. Well, this node is being deserted from both sides. So all the molecules in this football are going to the left. And the bigger the football, the bigger the displacement. And so at the antinode, that's where they are moving the furthest from equilibrium. Now, if this one's being deserted, the one next to it is being crunched from both sides. And this one's being deserted from both sides. And then a half period later, all of those arrows are going to turn around, every single one of them. And so this one right here, right now it's being deserted, and then it'll be crunched, and then it'll be deserted, then it'll be crunched, and then it'll be deserted, then it'll be crunched. That's the sloshing that makes the sound that goes across the room and attacks your eardrum. That's why you hear music come out of that organ pipe.
And how do you know like if it's short or long?
How do I know whether to draw the arrow short or long?
Yeah.
How close you are to the node. Okay, at the antinode where the football is fat, that's where you draw them longest. That's where the motion away from equilibrium is the greatest. The closer I get to that node, the closer I'm getting to not moving.
Is there any way to determine the direction of the arrows if you hadn't told us the one on the right is going that way?
No. Because it changes, you know, twice every oscillation. I have to give you one of the arrows.
You do a problem that is closed and open for an organ pipe and finding the length of the pipe.
Yeah. So let's say the third harmonic is, I'm gonna make this up, 200 hertz. Okay, and I want to know how long is that pipe? Well, the first thing you do is you draw a picture of the third harmonic. Well, the first harmonic has half a football. And that's going to be 200 hertz divided by 3. If F1 has 1/2 football, F3 has 3/2 footballs. There's a half, there's a half, there's a half. Okay. And so I use my football equation, 3/2 footballs times lambda over 2 is equal to L of the pipe. So if I knew lambda 3, I would know the length of the pipe, right? Well, how do I find lambda 3? Well, I always have this equation, and that works for every harmonic. In this case, the third harmonic. And that means that 343 meters per second is equal to 200 hertz times lambda 3. That gives me lambda 3 is equal to 343 meters per second divided by 200 hertz. And
1.7.
what's that?
1.7.
1.4?
1.7.
1.7? Okay. 1.7 meters. So now I go up here and I say 3/2 times 1.7 meters over 2 is equal to the length of the pipe. And then I solve for that. That makes sense? Now I could ask that backwards and say, well, the length of the pipe is 1/2 meter. What note does it play at the third harmonic? What frequency would the third harmonic be? In that case, I'd just work it backwards. I'd use the football equation to find lambda, and then I'd use the wave equation to take that lambda and turn it into a frequency. Okay. But I hope what you're seeing is that I'm using the same formulas over and over and over again. I'm using this formula, the grand wave equation, and the football formula. And with those two formulas, you can solve all the problems. It's kind of like the golden rules, love God and love your neighbor. Do those two things and you got the whole thing covered. Everything. Okay. Everything's good. We're gonna get 100%. Okay.
I had a question about beats, and sometimes I've come across equations where it mentions the frequency for one of the beats or for one of the
Sources.
and the other source, it just says like a certain amount of beats. And so when we're going to those problems, does the amount of beats equal a certain amount of hertz?
Yeah, the beat, when I say beats, I really mean beat frequency. And so if If say I'm tuning a piano and I'm plucking a particular string, and at the same time I'm playing a tuning fork. There's the string, and I'm playing a tuning fork that is a frequency of the tuning fork is 343 hertz. If I'm hearing 5 beats, what I'm really saying is I'm hearing 5 wah-wahs per second. Wah, 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 wah. Every second that goes by, I'm hearing 5 of those wah-wahs. And that tells me that the frequency of the string on the piano is going to be 343 hertz plus or minus 5 hertz. So that means it's either going to be 348 hertz or 338 hertz. Okay. Yes.
Can you explain the Bill and the Lane problem with like the beats?
Yeah, that problem is similar to the problem we solved yesterday in class that only had 2 possible answers. You know, with these boundary problems between 2 springs, the mother pulse either came in on the fast or it came in on the slow. So you guess and check. Well, in this case, there were 2 buzzers, and we were hearing 4 hertz beat frequency. Okay. And so I'm just going to make up some numbers here. Let's say that one of those buzzers had a frequency of 400 hertz, and the other one had a frequency of 404. Now, we want to know who has a higher buzzer, higher frequency buzzer. Is it Billy or Elaine? Well, there's only 2 possible answers. It's either Billy or it's Elaine. So let's take both cases. Let's say Billy has the higher one and Elaine has the lower one, or Elaine has the higher one and Billy has the lower one. Well, which one do you want to guess? Well, it doesn't matter. Let's guess this one here. We're told that as Elaine runs away from the campfire, those of us sitting around the campfire hear the beat frequency increase. It's not 4 anymore, it's 5. Okay. Well, if Elaine's running away from us, but Billy's sitting there by the fire, Billy's frequency doesn't get shifted. We still hear 404, but Elaine's is going to sound lower to us. Instead of hearing 400 from her buzzer, we're going to hear 399. And the beat frequency is just the difference between Billy's and Elaine's, what we're hearing. And so the beat frequency is going to increase. What we're going to hear is now going to be 5 hertz, 5 wah-wahs per second. So we guessed right. We're just lucky. We're just lucky. But if we had guessed wrong, if we had said, well, I think Elaine has the higher frequency, well, then as she ran away from us, we'd hear something lower than 404, maybe 403. Well, Billy's would still be 400, and now the shift would just be, the beat frequency would just be the difference, or would be 3 hertz. And so now, if that were the truth, the beat frequency we heard would go from 4 wah-wahs a second to 3 wah-wahs a second. We're told that it went higher, not lower. So Elaine had the lower and Billy had the higher.
Well, it doesn't matter if she's running away with constant speed or if she was accelerating, right?
No, regardless of how she's running away, the shift is gonna be down,
Okay.
okay? It's always gonna be down for away and above for towards.
Okay, thank you.
It's just the size of the shift that's determined by how fast. I may be damaged by all the years and years and years of teaching this, but in my mind, the exam on waves is just so much easier than the exam on rotation and fluids. And that's just, and over the years, and it's been many, many years, 33 years, the average is always higher on the exam on waves than it is on the one on fluids and rotation.
Set a new record.
Go over,
Lower.
thanks over different waves that we talked about, like longitudinal waves and transverse waves, like just all the waves that we've talked about this unit.
So the transverse waves are where the medium's moving perpendicular to the motion of the energy. And those waves happen on strings, springs, ropes, wave machines like this, that sort of thing. Longitudinal waves are like on a slinky or sound waves in a organ pipe. And in that case, the motion of the slinky or the motion of the molecules in the pipe are parallel to the motion of the energy. If the energy is going left to right, then longitudinal would be left and right, and transverse would be up and down. Now, that wave equation that works for traveling waves or standing waves. For traveling waves, it tells me how fast those crests are moving across from one place to another. For a longitudinal traveling wave, the 343 meters per second tells me how fast it's getting from my mouth to your ear, okay? Now that formula also works for standing waves, even though for a standing wave, nothing appears to be going left or right. But what we found with that little video was that this is caused by two waves interfering with each other, one going to your right and one going to your left. Okay, and as they pass through each other, I get this standing wave pattern. And that's why we can use that formula, whether we're dealing with standing waves or whether we're dealing with traveling waves. So really the way that you see the hierarchy, if we can put it that way, is right here. This works for all waves. This is only useful for standing waves. And when we're dealing with velocity, we always have two equations. And depending on what you've been given, that will determine which is most useful. So for longitudinal waves, whether they're traveling or standing, the speed is gonna be the speed of sound. And for transverse waves on a spring or a string or rope, it's gonna be given by this formula, square root of tension over the mass density. So if you solve for the speed here and plug it up into this formula there, you can, if you know the frequency, you can find the wavelength. If you know the wavelength, you can find the frequency. But those are the formulas for waves. That's just, there ain't anything else. And again, I've told you this over and over again. Those of you that are pre-med, you're gonna have to memorize all 12 bones of the body. This is nothing like that, you know? They're just 4 equations. My wife is a nurse practitioner, you know, and I asked her a question and, you know, what do I take for this? And she pulls out some long, complicated, ugly name that I can't even pronounce of some drug that's obscure that is in her head. And I can remember 4 things. Being a physicist is the best job in the world. I remember my children's names, F equals MA, these 4 equations, I'm good. Okay. Everything else is an owie. Other questions? Okay, I reserved the room for the hour, so I guess we'll stop here. I will post this to the YouTube site and send you a link. Good luck. If you get stumped, stop by my office, send me an email.
This semester.
Let me stop this here.
Might be going.
I'm hoping to TA for this.